distances. And what people have been doing is to divide here the smooth stellar halo from substructures in the stellar halo, in particular stellar streams. And for the smooth stellar halo, the steps are typically what I list here. You have to first assume that the entire system is in equilibrium. And then you have to adopt some parametrization of the dark matter halo profile. Assume again that the potential is static or slowly evolving. And then you have to adopt a symmetry for the potential, typically spherical or axisymmetric, with a fixed axis ratio or a varying axis ratio. And then you solve the Jeans equations under some assumption on velocity and isotropy, or assume that the traces follow some simple distribution function, which can be isotropic, or it can depend on the angular momentum. Then you feed the kinematics. Typically at large distances, we have only line of sight velocities, but this is changing with Gaia. We are starting to get also proper motions. And this is done out to some radius where you have data, which I'm calling R data. And then you want to extrapolate what you measure within R data to some fiducial virial radius, which is much larger typically than the volume where you have information. And I'm here highlighting the word fiducial because the virial radius is pretty much an arbitrary quantity that you can define in various ways, but it's still unclear whether it has some significance in dynamics, where the virial radius of the galaxy is. And then people also use stellar streams. Stellar streams are not in equilibrium. They are still phase mixing in the potential of the Milky Way. So because they are not in equilibrium, and here's one, you can see one of the main difficulties is that you have to introduce embodied techniques or techniques that are semi-analytical, like particle spraying, etc. You have to solve the orbits of many particles. Apart from that, you follow the same steps as for the smooth stellar halo. You adopt some dark matter halo profile, assume potential static or solve the volume, etc. And again, if you want to, because these streams tend to live in the inner regions of the Milky Way, the radius where you measure the mass is much smaller than the virial radius. And that means that you have to extrapolate what you find at small distances out to the outskirts of the galaxy in order to measure the total mass of our galaxy. So these extrapolations are always there, and they are, as you can imagine, quite dangerous. So this is a slide. I'm going to show you a paper from Wang et al. 2020, who very nicely compiled the Milky Way mass measurements for the last 10 years or so. He divided the measurements here according to the technique used. So you have, for example, using local high velocity stars. And the idea here is that the velocity of the stars in the solar neighborhood cannot exceed the escape velocity at the solar radius. So these guys, of course, all these are extrapolating the masses you measure at 8 kiloparsecs all the way out to 250 kiloparsecs. So the extrapolation here is quite significant. Still, they get the masses around 1.5, 10 to the 12. Then you have this work based on Leo 1. It's a satellite galaxy with very high velocity at large distances. And the idea is that people think that, you know, if you want to have this galaxy gravitationally bound to the Milky Way, then you put a constraint on the total Milky Way mass. Although this condition, I think makes little sense in a cosmological context, whether or not satellites are gravitationally bound or not. And we can talk about that later if you want. Then you have, of course, a circular velocity of the Milky Way, and then you can extrapolate that. This is a relatively straightforward derivation of the mass from the circular velocity of our galaxy, but of course this stops roughly at 25 kiloparsecs. So it's again an extrapolation of the order of 10, factor 10 in radius. And then you have the Jeans equations, the distribution functions, again masses between 0.5 and 4 times 10 to the 12. So there is a factor 4 in mass here using different techniques. Now it's worrisome that some of these techniques use the same data. So you have very different values depending on what technique you want to use, even if the data is very similar. Same with tidal streams, you know, covering a very large range of Milky Way masses. And now you have here the timing argument. This is what I'm going to talk today. And you can see again that there is a very strong discrepancy between the values I'm going to show you today, which are roughly here, with the values that Lee and White got in 2008, and then later Son et al. As well. So I'm going to focus on these on these points in this talk. And then you have satellite galaxies again, which similar with, again, use satellite galaxies as tracers of the underlying dark matter potential. Okay, so what is the reason that that Lee and White was getting such a high Milky Way mass of the order of 2.5 10 to the 12 solar masses? And so this is what I'm going to be showing you is the data, so the dynamics of local group galaxies, galaxies between 0.8 and 3 megaparsecs from the local group. And you can see here the raw data. This is from McConaughey et al. 2012. You see a very striking relation between distance and velocity, which is very reminiscent of the Hubble's law, right? You see that from some radius, from 1 megaparsec, the velocity increases in proportion to distance. So when I saw this, I thought this was very interesting. So how can we model this data? So I went back to the literature and I realized that people usually have used this differential equation. This is a modification of the Robertson-Freeman equation. Instead of a constant density, now you have a point mass perturbing the expansion of the universe. It's a second order differential equation. So you need two conditions. At the time of the Big Bang, t close to 0, you have is that all the particles in this model are infinitely close, and they are all moving with positive velocities relative to each other. This is what we call the Big Bang conditions, the initial conditions. And this very simple setup provides actually two ways to measure the local group mass. The first one was introduced by Kahn and Voltaire in 1959, and used the relative motion between Andromeda and the Milky Way. This is what I'm going to call the timing argument, or the classical timing argument. But then Donald Lindenbell, later Alan Sandage, used this differential equation also to model the dynamics of galaxies around the local group, right? And that's the technique I've been using. And this is an example of how these equations, what kind of predictions these equations are making. So here, the only thing I'm doing is to integrate this differential equation for a very large range of initial velocities, all of them positive. So because you have the Big Bang, the expansion, what you see is that particles start to move to larger and larger radii. But if you pay attention here, you will see that some of these particles reach the apocenter or the turnaround. You see here this ring, and then they start to fall back. And they fall back due to the gravitational attraction of the point mass, the red dot. If you plot these particles in phase space, so velocity and distance, what you see here is that they have this feature which we call isochrones. And they are isochrones because we are integrating all these particles for the same amount of time. So you can stop the isochrone close to the present time, and this is the kind of feature you would expect in phase space density. So this is remarkable, similar to, if I go back to what we were seeing before, right? This looks a lot like what the data is doing. So when I saw this, I thought, well, it's going to be great to try to derive the local group mass by fitting the observational data in McConaughey et al. 2012. So to do that, the main difficulty really is that the sun is not located at the barycenter of the local group, and that we really don't know where the barycenter is located. So we have to make assumptions, and the main assumption that I made was that the Andromeda and the Milky Way dominate the mass budget in the local group. So under that assumption, the barycenter would be located at some point between these two galaxies, and the location along this line will depend on the mass ratio of the two galaxies. So you can fold that in and then take into account that the sun is moving with respect to the Milky Way. So here you have some circular velocity at the solar radius, the local standard of rest motion, and then the motion of the sun with respect to the barycenter can be encapsulated in this formula I'm showing here, and depends on the mass ratio of the two galaxies. So this is a very simple way to try to pin down the location of the barycenter. And the main uncertainty, as you can imagine, is the mass ratio between the two galaxies, Although in my analysis, I allowed to V naught to be free. So flat prior on V naught, because I wanted to know how well we can actually constrain the circular velocity of the sun around the Milky Way using external galaxies, just for fun. And so you can now think, how are we going to get any constraint on the barycenter of the local group? And this is why we can get a constraint on the barycenter, because if you change the mass ratio of the Milky Way and Andromeda, the way that the Hubble flow looks will change. If you change the barycenter, then the radial velocity changes. And what you see is that depending on the mass ratio you assume for the two galaxies, the Hubble flow might look hotter or colder. So the argument here is that that the Hubble flows should be as cold as possible, and that if you find hotter Hubble flows, it's because you are not choosing the right mass ratio. So we can fit all these quantities simultaneously: the mass of the local group and the mass ratio between the two galaxies, V naught, the circular velocity of the sun. And then I even allow the omega lambda and the Hubble constant to be free parameters, so completely flat priors on all these quantities. And what I found is that it's a really nice fit, and there are no outliers in this fit. I was getting a constraint on the local group mass of the order of 2.3 times 10 to the 12 solar masses, which is factor 2 smaller than Lee and White 2008 value. Mass ratio of the order of 1 to 2. So the Milky Way is approximately half the mass of Andromeda. The value of V naught is actually consistent with Gaia values. It's much more uncertain, as you would expect, because we are only using 35 galaxies for this fit. But it's nice that it's consistent with the values that you will find nowadays. And we also get the constraint for omega lambda and H, but actually there's a very strong degeneracy. I can show you the posteriors later if you're interested. What we can actually constrain with the local group is the age of the universe, which is 13.2 plus minus 3 gigayears. Again, it's relatively uncertain compared with CMB constraints, but it's fully consistent. So if we now say, okay, if we put a constraint put a bound on the omega lambda based on CMB, what is the value of H naught that we would get from the local group? And this is the histograms of the posterior distribution. So again, you can see center at the CMB value of the order of 67 kilometers per second per megaparsec. Sorry, sorry, the units are wrong. And that was really nice. So in principle, we are consistent with lambda CDM cosmology all the way to the local group scales. The only problem we found is that when you put Milky Way and M31 in this diagram, remember that it's the same equations, differential equations for the M31 and the Milky Way as for the rest of the galaxies in this plot. But what you see is that they are not consistent. This is what people found from the timing argument is not consistent with the fit to the local group dynamics. And at the time in 2014, we didn't understand this result. And there was no clear reason why M31 and Andromeda, the relative motion should be such different from the rest of from the local group. And the difference between the predicted value and the observed value is significant again. So it's of the order of 2 sigma. So yeah, at that time, we didn't understand what was going on. And then, I was at a conference with Facundo Gomez, and he was talking about the LMC. And then he showed me this plot. I say, well, the LMC might be falling in now. And the question is if the LMC was accreted recently. This is just, by the way, sorry, I should mention, this trajectory is back in time. It's what Facundo was measuring by integrating backwards the motion of the LMC suggested by HST measurements of the proper motion of the LMC. So if you take those proper motions and the radial velocity and integrate backwards, what you find is that most likely solution is that the LMC is falling in now, and that it crossed the virial radius of the Milky Way only 700 million years ago. So this has been a really recent accretion event, according to these models. So the question that Facundo posed was, well, do you think that the NMC can affect your measurements of the local group mass? And I thought that was a great question. So we worked together on this, and what I did was to slightly change the previous method I was showing you. So what I did was to relax my assumption that the barycenter of the galaxy is at the center of the Milky Way, which sounds like a crazy thing to do, but if the NMC is massive, then we should expect the barycenter of the galaxy in between the NMC and the Milky Way. And then again, this can be encapsulated in this formula by adding this component to the equation, which takes into account the mass ratio between the LMC and the Milky Way. This is the FC parameter. So FC, you would expect FC to be much smaller than 1, okay? So it's not clear, it was not clear at the time that we would be able to see a visible effect, because I was expecting this quantity to be, or this entire component here to be much smaller than the rest. But the point to take here is that the velocity of the NMC that measured from the proper motions is huge. So the NMC is moving at 370 kilometers per second now. And of course, this is a very large quantity. So even if FC is small, this can still lead to a significant contribution to the apex of the sun with respect to the barycenter of the local group. So, okay, so very simple. How is that the presence of the LMC, this component, might affect the timing argument mass? So this is just taking into account the relative motion between these two galaxies. So here you see the timing argument mass versus FC, the mass ratio between the LMC and the Milky Way. And what people like Lee and White were assuming is that this parameter is 0. So if this parameter is 0, we recover their measurements, obviously, around 5 times 10 to the 12. But if FC is not 0, and in particular, if FC reaches 0.2 or beyond, then what you find is that the mass of the local group is closer to 3 times 10 to the 12 solar masses. Also, the apocenter is not as small as people expected in the past. So it's not going to be a head-on collision anymore, according to these corrections. So this was interesting. So what I did next was to fit the local group dynamics and the timing argument simultaneously. And that was quite a lot of fun in this paper, because we get a simultaneous measurement of the LMC mass, the Milky Way mass, and Andromeda masses. These are the numbers we got. So the mass ratio is not 1/2 anymore, but closer to 1/3, as you can see here. The mass of the local group is similar. Before we got 2.3, and now we get 2.6, which is within 1 sigma value. So adding the LMC doesn't change the local group mass we were getting. But what we got is a very large LMC mass, 2.5 times 10 to the 11 solar masses. And when we got this, we thought this is kind of crazy. This is a very large value. But actually, if you compare with abundance matching constraints, then this is exactly what you would expect for a luminosity of the LMC. So for around 3 times 10 to the 9 solar masses in luminosity. So I have to say that from these results, what this is telling me is that in principle, lambda CDM has no internal contradiction. We can explain the dynamics of the local group. And the value of H0 we get is what you would expect from the CMB. Now with the timing argument and the local group dynamic gives you the same values, so very similar values for the local group mass if you assume that the LMC is as massive as this. So this was interesting. But there are very important implications, as you can see. Now, what we are claiming is that the mass ratio of the LMC could be 20%, and then LMC is located well within the Milky Way at 50 kiloparsecs from the center, and the infall time was relatively recent. So that led us to think that the LMC might introduce very strong perturbations on the Milky Way disk and the halo, and it's going to deform tidal streams and therefore bias our inference of the dark matter potential very likely. And there's been a lot of papers last year pointing in this direction. So what is then what we can do if you drop the equilibrium assumption? I think we are bound, and there is no other way I can imagine but running live n-body models that follow this interaction. I think unfortunately I think it's going to complicate any analytical treatment of the data. So this is a very schematic view of the interaction that we were getting in the live and body simulations. Of course, those simulations are much more spectacular than this, but here I'm highlighting a very important point, is that the LMC is coming in red, as you can see here. The Milky Way disk is this thing in blue. The arrow points in the motion of the Milky Way disk. So from this model, it was becoming obvious that actually one of the effects of the LMC is going to be to displace the Milky Way disk from the barycenter of the galaxy. And it's going to be moving in some directions with respect to the outskirts of the dark matter halo, right? Because you have to imagine that this motion, as this movie is showing, is very fast. Most of the motion of the disk happens within the last 0.3, 0.4 gigayears. So this is still much shorter than the orbital period of many stars and dark matter particles in the stellar halo. So that's what we learned from these live and body simulations. So this is a measurement how different the disk is moving with respect to the dark matter halo. If you look at the bottom panel, you see is the velocity of the disk and the velocity of the halo. Now you see is that there is a big difference between the disk and the halo motion. So the disk is moving with respect to the dark matter halo and also with respect to the stellar halo. So this is the prediction that we expected, right? If we are moving, the sun or the Earth in the solar system within the Milky Way disk is moving with respect to the stellar halo in some particular direction. So this is the kind of effect that we envisioned last year. Sorry. We would expect this kind of reflex motion, the apparent motion of the stars in the stellar halo, this due to the motion of the disk. And the effect will be very similar to what you see here in the Star Wars movie. So you would expect some apex direction here, and then as you move away from the apex, what you see is very strong tangential motions. So this, we last year during the first lockdown, we thought, well, what can we do best but trying to measure this effect? Now we had the Gaia DR2 at the time. We looked for stars in the Gaia catalog with full 6D information. So we got 543 K-giants, 292 BHPs, and 33 satellites with full 6D information beyond 40 kiloparsecs. And the choice of 40 kiloparsecs is because from this radius to outwards, the orbital period is larger than 0.7 gigayears. So we think that the stars beyond 40 kiloparsecs will react impulsively to the LMC info. See, these are the kind of errors you expect in Gaia. K-giants are much, much better, much more accurate than BHPs. If you are wondering, these are the RLR stars. So in number, we have huge number of RLR stars, around 10 to the 5. But we found that only 100 have radial velocity. So this is a huge opportunity here. I mean, the vast majority of RLR stars in the stellar halo do not have radial velocities available. So we had to use the K-giants and the BHPs and the satellites. So then we did some Bayesian fit of the global kinematic pattern you would expect if the Milky Way disk is traveling through the halo. So this is the V travel component. Then we allow the halo to have some mean radial motion, expansion of contraction, and rotation. And then we had to correct for the solar reflex motion. So this is the kind of quantities we fitted here. And something I wanted to point out, which was very, very important, is that it would be difficult to distinguish the top model, which is a dipole, basically translation, the motion of the disk, from pure rotation in the stellar halo. So you see that the line of sight velocities map will look very similar. The tangential map in the vertical component will be very similar. And the main difference will be in the azimuthal component of the velocities. By the way, this black line is the SDSS footprint. So you can see that we have mostly access to the north. Okay, so 3D kinematics are really important in this analysis. That's why we chose only stars with 6D information. this is just the likelihood, how it looks. We can discuss that later if you're interested. This is the results. So a couple of slides more. And we found a measurement. So we found that the disk was moving in this direction, which seems to point along the trajectory of the LMC, but in a past trajectory. Not so you see that the LMC is here. So it's almost pointing to the other side of the galaxy. And if you're wondering where this area of the sky is, this is pointing to M31. So M31 is around here. This is the Pegasus constellation. So, and interestingly, all our tracers, BHBs, Cape Giants, and the satellites seem to give us the same answer, that the disk is moving in this direction with respect to the tracers. For the future, by the way, this is very interesting because, you know, we can get, this trajectory is heavily dependent on the distribution of dark matter in the Milky Way and the LMC as well. so this is interesting for follow-up work. This is the amplitude of the reflex motion is of the order of 35 kilometers per second, which is exactly what we expected for this particular mass range between 0.1 and 0.2. So I would say that this is evidence for disequilibrium. And with this, I'm giving you my summary because I'm running out of time. So the first part of the talk showed that the local group in a cosmological context, that this is really nice. We have very few number of stars, only 35 kiloparsecs in this range of distances. But even with 35 kiloparsecs, we can get really interesting constraints on the main masses, on the masses of the main galaxies, Andromeda and the Milky Way, and as well as the LMC mass. And we can also fit the cosmological parameters, everything simultaneously, which is very good. And we don't have to make any equilibrium assumption, and we don't have to adopt any dark matter profile or shape for the Milky Way or Andromeda or the LMC. So that's another nice aspect. I show you that the classical timing argument, the reason that people like Leon White was getting such a high local group mass might be due to the basically that they didn't consider the LMC at all. And if you consider the LMC, then everything seems to fall so everything seems to be consistent if you adopt a mass ratio of around 1 to 5 for the LMC Milky Way mass ratio. Then I show you that one of the main predictions from life and models that follow the accretion of the LMC is the displacement of the Milky Way disk from the Bary center of the Milky Way, and that we have found evidence for this being the case, and that the disk motion points to some past point along the trajectory of the LMC. And if you give me one more minute, I'll show you a couple of slides for stuff that I've been doing with Mike, and I'm sure that he's going to continue this work when he comes to Paris. So the first one is follow-up. So I was telling you that the outer stellar halo will respond impulsively, but this is only true beyond 40 kiloparsecs. So what we did was to repeat the measurement in different radial beams. What we see is exactly what we expected. Lines are the prediction from life and body simulations. These will be the theta and the phi components of the apex direction. Now you see is that the apex is moving on the sky. And we believe this is due to the response of the stellar halo at small distances. So what you see is some projection of the global motion of the global response of the stellar halo. For this radial range, the stellar halo has time to respond. The orbital periods are smaller than 0.7 gigayears. So we see some of that. And that the V travel also changes with the amplitude of the reflex motion, also depends on distance. And again, it's very much as expected from the models, but you see some discrepancies. And this might be due to contamination at the small distances, between 20 and 30 kiloparsecs. We have to be more careful in choosing our tracers to avoid this contamination. And also the presence of substructure. So that's what we are working on right now, trying to understand this selection better. And then Mike is running embodied models that follow the response of the Milky Way disk to the LMC in fall, which is very dramatic, as you can see in this movie. So let me show it again. So the arrow points to the LMC, of course. What you see is we are very close to Bary. So in Mike's models, this will be the current state of the Milky Way disk. So you can see it's very heavily perturbed, especially in the outer region. So this is something we want to compare with Gaia data in order to get better constraints on the Milky Way disk. And if you continue the evolution forward in time, what you end up is a Milky Way disk that is much puffier than what we assumed up initially. So I think it's a good time to finish. Sorry, I went a little bit over time, and I will be very happy to take any questions. Thank you.
Thanks a lot, Jorge. No, you were perfectly on time. Thanks. Any questions? We have one from Nick. Thanks for your talk. It was great. I really enjoyed it. By the way, yeah, you're unmuted, Nick. Go ahead.
I am. Oh no, not anymore. You hear me?
Yes. Hello.
Very nice talk. Thank you. So I probably missed it on your table of all the results, but I'd have thought one thing that really stands out in the history of this is the least action modeling that Jim Peebles did.
Mm-hmm.
And I was intrigued when you found that the M31 Milky Way velocity doesn't fit with your model, because as I recall, what he does is he actually uses that as the single datum to tie down the model.
That's right.
Which then predicts the velocity of all of the other neighbors. And I thought his conclusion, he found that it actually works very well. But so he's doing it in the opposite direction to what you're doing. You're using the velocity of the neighbors to fix the model and then comparing with Andromeda Milky Way velocity. So why don't...
in this particular case, I didn't go from any direction. I did the fit simultaneously. So here in this analysis, I'm fitting the M31 Milky Way and the local group Galaxies simultaneously. So that's why I can get a constraint on all the masses involved in the problem simultaneously. So I was not anchoring any measurement. Everything has flat priors in my analysis.
I was referring to your earlier result, right?
The earlier result. This one.
This one, yeah.
Yeah, this one neglected entirely M31 and the Milky Way. So this is the fit that I would get only for local group galaxies. That you are right. But here you can see directly what the velocity that the Peebles used, right? The minus 171 kilometers per second is down here. Is much higher than you would expect at this distance.
Well, he uses, I mean, he just needs one velocity to fix the model.
Right.
He uses that, but then the model predicts all the other points on this plot.
No, I'm surprised about that because, I mean, it's very, very simple to solve the differential equation. And actually, Donald Lindelbelt solved it analytically, and you can show that if you assume 5 points times 10 to the 12, you can see in this plot that you are going to get a line down here, right? So that was very clear from the beginning that the local group could not, with 10 times 10 to the 12, you are really, I mean, the discrepancy is quite obvious, even by just overplotting the analytical model on top of this data. I'm not sure. I will have to go back to Peebles and see exactly how well he was constraining this thing.
The other question I had is what's the motivation for wanting to make the scatter in this plot as small as possible?
Well, because the underlying assumption here is that the Hubble flow is very cold, and that the scatter you would see is a combination of errors plus some hyperparameter sigma square. And what the likelihood is doing is that we know that if you choose the wrong location of barycenter, that the Hubble flow will become hotter, but this is artificial. It's just a wrong selection.
But the Hubble flow can be cold, and any tidal field will the likelihood. You're effectively saying the external tidal field has to be zero, I think.
No. Oh, sorry. I think that was me going too fast. So what I have here is a let me see whether I can find the likelihood of this thing. No, not here. But basically, I have a parameter that measures how cold the Hubble flow is. It's not zero. It's some velocity.
Right.
It turns out to be around. Okay, I think I have a plot here. So is this? This is the hyperparameter that measures how cold the Hubble flow is. So you add this in quadrature to the errors, and you end up having around 50 kilometers per second.
Yeah, but I still don't see why it should be minimized. If there's an external tidal field from the Virgo supercluster, for instance, that'll produce something which on a radial plot will look like an extra scatter.
Yeah, I think the argument here is that this extra scatter is due to the wrong choice of the Bary center. Or in other words, if you choose the wrong location of the Bary center, you increase the scatter.
Right. No, I understand that. Yeah.
Yeah. So you can turn that argument around, and we can agree or disagree. But what this method is doing is to try to minimize that particular scenario where the scatter is partially due to the wrong choice of Bary center. I think it makes sense, but I'm not making any prior assumption of how hot it should be. This is something that comes from the measurement.
Well, that's certainly consistent with the uncertainty, isn't it?
Yeah, exactly. It's very much consistent. So we get 50 kilometers per second, and that's, it's close to what the uncertainties at those radii are. So you might argue that it's consistent with zero, but the fact that this hyperparameter is not zero at 5 sigma or more is telling you that there is some scatter in the Hubble flow.
Okay, thank you.
Because if this was zero, then it means that this scatter is purely due to errors, and this is not what this parameter is telling
you. Gary, you can go ahead.
Okay, wonderful work, Jorge. Thank you very much.
Thank you.
So, okay, a quick question first, and then a more general question in line with what Nick asked. What about the SMC? So is that combined with the LMC when you give the mass fraction?
Yes, you were not the referee, were you?
No.
So I think what happens is that you look at this equation, for example, you can add the SMC into this framework.
Exactly.
And then you will have basically the mass ratio between the SMC and the LMC, which is another factor 0.1. So you will have a factor FC times F SMC if you want.
Oh, it's that small, the SMC compared to the LMC? I didn't know.
Yeah, at least from the internal kinematics, we expect more or less 1 to 10 mass ratio between the LMC and SMC.
Okay.
So we neglected the SMC, but you are right that this will be quite.
But yeah, you can say they're orbiting each other and just estimate them as a sum of two things.
Exactly. You would say, okay, the Bary center is the same argument. The Bary center is not located at the center of the LMC, will be between the SMC and the LMC, and then you repeat the same or very similar analysis. But I think I did check that, and the value you get is very small correction to what we find.
So then I have a more philosophical question, which might imply that I really don't understand dynamics, which is very possible. And,
I don't think so.
No, but you'll be surprised at my lack of understanding of things. And it's the fact that we live in a universe which at the beginning was quasi-homogeneous. And you could solve the local group dynamics in two frames. You can either do it in physical coordinates or in co-moving coordinates.
Yes.
If you do it in physical coordinates, what happens is that, let me get this right. In physical coordinates, your systems are, how can I say this? They're very smooth, right? So they have very flat density profiles, okay? And at least an absolute value. And then in co-moving coordinates, their masses are changing.
Mm-hmm. Yeah.
Okay. So is all this legitimate? It must be, since we do simulations, right?
Yes, it took me a while.
So, for example, in the Peebles action method, he assumes that at least at first, he assumed that the galaxies were fixed point masses. Okay, and that bothered me. And in fact, I was also bothered by the fact that he found that the relative velocity of Andromeda to us had a greater tangential component than the radial component, which I think is not borne out by recent data. But you know this better than me.
No, I include the tangential velocities in this analysis as well. So they are small. The apparent velocities are small. Yeah, so to be honest, I teach all my students to use physical coordinates because I think they've been staring at so many movies with incomoving coordinates that they get surprised when they say, "Oh, but this thing is expanding." Yeah, in physical coordinates, everything is expanding. That's right.
Yeah.
But there are subtleties, you are right, philosophical ones, like, for example, why this mass is not allowed to vary in my models and things like this. And what is the mass that the timing argument is measuring? Or the mass that I'm measuring is not the virial mass, right?
Exactly.
So I didn't have time to show this, but I'm going to show you one plot, because, you know, we did with Asi Fatahi, we look at the Apostle simulations and we apply the same method. And this is what we found, is that these very simple equations describe real embodied simulations super well. We didn't find any single outlier in the 12 simulations we analyzed. So, and then we compared the masses and we found that the timing argument masses on the y-axis are different from the combined virial masses. So the timing argument mass, or the mass you derive from the local Hubble flow, is systematically larger than the virial mass. And this is no surprise if you think about it, because dark matter halos are not truncated at the virial radius. There is more mass beyond the virial radius. And this is being picked by the local group dynamics. So there is a lot of things to, and then the referee was asking me, but then can you derive the virial mass from the Hubble flow or not? And I was thinking, well, but the virial radius is completely arbitrary. So that question is the same as saying, can you derive the dark matter profile from the Hubble flow? And I think that's not possible. I think it's very, very difficult. So I think from cosmological data, we can get an idea of the total mass of these objects, but not the profiles of these objects.
So this mass is about twice as much as the virial mass, and therefore you're measuring something more like the mass within the backsplash radius, or maybe the turnaround radius, more like the backsplash radius.
Yes, it's not completely clear, and we are repeating this experiment with students here. The last year projects. We are repeating that with the clusters of galaxies, and then you can apply this methodology to cluster of galaxies, trying to understand what is the mass that are perturbing the Hubble flow. And again, it's not a virial mass, so I don't know. I think Nick Kaiser, you probably know more than me, but this connection that people do in cosmological simulations of analyzing virial masses is, there is some missing step in between to connect those virial masses with what the expansion of the universe and the way the structures grow. And I don't know whether that's taken into account at what level, but yeah, certainly from these little experiments, they are not the same things.
Great, thanks.
Any more questions for Jorge before we conclude?
I have a small comment on this last question. Hello, I'm Elena, the new postdoc at IAP.
Yeah, I was going to introduce you to the group just after that.
Okay, so sorry, just I have the small comment. So I work on the application of the least action principle of Peebles on cosmological scales. So maybe I can comment on the fact that we conserve the mass of the objects going back in time. And I think there is a detail in the action of Peebles. So to be able to compensate for the Hubble flow, we assume that the tracers we observed are accounting for all the mass of the universe. So we assume a bias scheme. So in some sense, we correct the masses of the objects to already account for all the density. So in moving coordinates, if we consider a simulation and we go back in time, we conserve so that the density stays constant. So we have the mass that can stay constant. So it's kind of equivalent of assuming that the halo bias scheme of the tracer at the observed redshift stays the same as back in time. So it's just an approximation because people actually has to conserve the number of objects. That's the detail.
And Elena, in that scheme, the mass, is that the virial mass or is any mass? Do you try to make a connection with the virial masses?
So it depends. So on cosmological scale, because for example, I'm interested now in the BAO, I use only the number density, then apply a bias scheme, and then I translate that into, so that I have it's the mass within just the radius of the over density, the peak of the over density. But then my masses are point-like masses, so it's not connected to virial masses. Now I'm applying it to astrophysical scales. So I'm like on a smaller scale, say 100 megaparsec. And what I found that actually the virial mass is not sufficient. But if you use Air max, so you use a definition of the radius of a cluster or a galaxies that actually accounts for the potential, for the shape of the potential around the cluster, then you can find that you can recover the velocity of the objects quite well.
Okay, interesting.
But R200, R500, and BR radius are too small, for at least for my assumptions.
Nice. If you can send me a reference, that would be great.
Sure. I'll be happy.
So thanks for the nice transition, Elena, and welcome. Let me take the opportunity to welcome you in the group. So Elena is officially, I think, starting today. Roya told me, and working with Roya as a postdoc, and she did her studies in Marseille with Carlo Schmidt. So welcome, Elena. And as a baptism of fire, I think I'll bug you to give a talk soon, as soon as you want.
With pleasure. With pleasure.
Sorry for the hazing practice here.
No. So thank you for having me here. It's very nice. I'm very happy to be here.
All right, so let's thanks Jorge again for this great talk, and have a good day, everyone.
Thank you.
Bye-bye. Have a nice day.
Bye.
Great.
Bye. Take care.
Take care, Jorge.
Take care, Gary. Hopefully we'll see each other soon.
Yes, I hope so.
See you, Roya.